Hello everyone, welcome to the class. In last class, I introduced you grating. There we talked about grating equations, and we saw that the grating can work in two modes. First is called transmission mode, second is reflection mode. The grating which work in transmission mode we call them transmission grating, while the grating which work in reflection mode we call them reflection grating. And we also saw the grating equation for the normal and oblique incidences, and then we saw that we can also shift the energy from a particular order in a grating to some order, some given order or some other order of a grating by just incorporating blaze or some initial tilt in the grating element. Today we will talk about the most important application of the grating, which is in spectroscopy. Okay. And here we will talk about grating spectrum and its resolving power. Now, grating spectrometers are used over the range from soft X-rays to the far infrared. It all depends upon the grating element. For different wavelength, we will have to just tune the size of the grating element. Now, assume an infinitesimally narrow incoherent source. Okay, suppose we have a source which is very narrow, okay, as narrow as possible. Okay. The effective width of an emergent spectral line may be defined as the angular distance between the zeros on either side of the principal maxima. Okay. Because suppose we have a line and then it is forming a pattern. Since it is infinitesimally thin, then what will happen? It will create a pattern with some central maximum here. Okay. And if we want to calculate the width of this principal maximum, then we will have to calculate the angular positions of first minima on the either side of principal maxima. Okay. Now, we know that in many slit diffraction patterns, since we are talking about grating, therefore, we will this grating is always, we will always correlate the grating with the multiple slit diffraction. Okay. Now, in many slit diffraction pattern, we know that the positions of minima are given by plus minus n plus minus 2 pi by n. These were the positions of minima in multiple slit diffraction pattern, yeah, plus minus pi by n, plus minus 2 pi by n. Now, these positions of principal maxima allow us to calculate the angular separation of minima on either side of principal maxima. How can it be calculated? For the first minima, which now be located at position plus pi by n here and minus pi by n here. Now, if you want to calculate its angular width, just subtract these two angles. Okay. The one angle is given in this direction, other angle is given in this direction, just calculate the overall angle. Okay. The overall angle here in this case would be pi by n plus pi by n minus of minus pi by n, which would be equal to 2 pi by n. Okay. And this will give us the angular distance between the zeros on either side of this maxima, okay, and which we designate by delta alpha. Okay. Now, for oblique incidence, this alpha can be redefined. Okay. The usual alpha is K A sin theta by 2, but this condition is only for normal incidence. For oblique incidence, this term would be added minus sin theta I, as we also did the same in grating equation. Okay. Now, with this modified alpha, we can calculate the change in alpha or a small change in alpha. How to calculate it? We just differentiate it. Okay. Now, if you differentiate equation number 40, where theta is the angle of incidence which is fixed, then you will get K A by 2 cos theta delta theta. Okay. This is what is given here, delta alpha is equal to K A by 2 cos theta delta theta, and which is nothing but 2 pi by capital N. Okay, this is therefore, we are equating it here with 2 pi by capital N. Now, angle of incidence is constant, therefore, we have neglected delta theta I. Okay. Now, thus even when the incident light is monochromatic, here we are assuming that there is a single wavelength source, we have some spread in theta which is delta theta, and this delta theta from equation number 41 can be expressed in form of equation 42, which says that delta theta is twice lambda by N A cos theta m. Okay, and this is the angular width of a line due to instrumental broadening. Okay. The instrumental broadening means that this width has nothing to do with the wavelength spread in the source, because even when there is only one wavelength in the source, there would be some spread which is here being measured by delta theta, and therefore, this spread is named, or this spread owes its origin in instrumental broadening. N is the number of slits and A is slit to slit separation. Okay. A starts from center of one slit and it goes to the center of other slit. Therefore, N A would be equal to the length of the grating. Okay. N A is the length of the grating L. Now, there is another very important parameter which is called angular dispersion, and it comes when our source is non-monochromatic. Okay. We calculated this angle, the angular spread for sources which are monochromatic, because we cannot have monochromatic sources in real life. Okay. All the sources, the real sources, they have certain wavelength spread. Okay. But consider or assume that there are a source which is monochromatic, still in that particular case there would be some broadening, which we call instrumental broadening. But what if the source has some wavelength spread or bandwidth? In that particular case, we define angular dispersion, which is designated by this italic d and is defined as d theta by d lambda. Okay. Now, if you remember, the grating equation is given by A sin theta m is equal to m lambda. Now, if you differentiate this grating equation, then you get m cos theta m d theta m by d lambda is equal to m. From here, d theta m by d lambda would be m by A cos theta m. Now, this is nothing but your angular dispersion d. Okay. Therefore, this is for grating. For normal incidence, we can again write this expression for angular dispersion in a modified form, and this equation is again valid for oblique incidence too, because the angle of incidence is fixed. Now, this means that angular separation between two different frequency lines will increase as the order increases. Yeah, you see that order is sitting here in the numerator, and d is nothing but delta theta by delta lambda or d theta by d lambda. So, as m increases, d theta also increases. Okay. It means angular separation between two frequency lines will increase with the order. Now, apart from this angular dispersion, there is one more important parameter which we should know, and this is known as chromatic resolving power R. The chromatic resolving power of a spectrometer is defined as lambda by delta lambda min. Okay. Lambda is the average wavelength of the source. Okay. Suppose the source has several wavelength, that lambda is average of that, and delta lambda mean is the minimum resolvable wavelength separation. Okay. The delta lambda mean is the least resolvable wavelength difference. Okay. And there is another name of this delta lambda mean, and which is limit of resolution. Now, once the limit of resolution jumps into the discussion, then we also talk about what is the criteria of defining the resolution. Then again Rayleigh comes into the picture, and Rayleigh gave a criteria which is the same criteria which we discussed in case of multiple slit. The criteria says for the resolution of two fringes requires that the principal maximum of one coincide with the first minimum of the other. Okay. At the limit of resolution, the angular separation is half the line width. I will reread it. For the resolution of two fringes requires that the principal maximum of one coincide with the first minimum. Suppose there is a fringe pattern which has maxima here, then the two wavelength which are forming their diffraction pattern at a some screen at a some angle, if the principal maxima of one falls on the first minimum of the other, then only the two wavelengths are said to be resolved or just resolved. Okay. If the separation is larger than this, then they can easily be resolved. If the separation is smaller than this, then the instrument cannot resolve it. Okay. Delta lambda mean is the minimum, the least resolvable difference, and it happens when the maxima of one falls at the first minimum of the other. Okay, and this is called the limit of resolution. And at the limit of resolution, the angular separation is the half the line width, because this is our source and this source generate a principal maximum, and this is the first minimum of the principal maximum which is on the either side of the principal maximum. Now, on this first minimum, the principal maximum of the other wavelength is falling. Therefore, this angle, this would be half of delta theta which we measured here in equation number 42. Okay. Therefore, at limit of resolution, the angular separation would be delta theta by 2, which we call as delta theta min. Okay. And this is what is defined here. At limit of resolution, the angular separation is half the line width. Okay. Delta theta is your line width, and hence from equation 42, the equation which I showed you a minute before, delta theta minimum would be lambda by n a cos theta m. Okay. This is coming from equation number 42. Okay. Just we divided 42 by 2, and then we have this equation number 45, which defines the angular separation at the limit of resolution. Okay. This is angular separation at the limit of resolution. Now, once this is known, from again equation 43, we can calculate delta theta upon delta lambda. Okay. 43 is here, which is angular dispersion. Now, delta theta upon delta lambda is m by a cos theta m. Okay. We have this expression and we have this expression delta theta mean, which is nothing but lambda upon n a cos theta m. Okay. If you divide these two expressions, then you get lambda upon delta lambda mean, which is this chromatic resolving power lambda upon delta lambda mean. Okay. Therefore, chromatic resolving power, it is given by small m into capital N. N is the number of slits in the grating and m is the diffraction order. The chromatic dispersion power is therefore equal to n m into n, capital N, and it can equivalently be given by this relation, which is n a sin theta m minus sin theta I by lambda, where we have used grating equation to replace m. Okay. Now, what is the maximum possible value of 48? The maximum possible value of resolving power would be n a by lambda, or sorry 2 n a by lambda, yeah, it is a small a here, 2 n a by lambda. How to calculate it? This will occur when angle of incidence is 90 degree, okay, and when it is equal to angle of diffraction. With this we will have value of sin theta m is equal to 1, while the value of sin theta I is equal to minus 1, or vice versa. Yeah, we will have this bracket would be equal to 2, and from here we get the maximum value of this resolving power as 2 n a by lambda. The minus sign which is here appearing here, it is only due to the fact that theta I and theta m are on the same side of the normal. Okay. Thus, what we saw is that analogous to multi slit experiment, we can define resolving power, we can define delta theta mean. Okay. Now, suppose we are given two lines of wavelength lambda and lambda plus delta lambda, which are very closely spaced, and their successive orders of course would be m plus 1 and m, and these successive orders we assume that they are coinciding. Okay. Now, if two lines of wavelength lambda and lambda plus delta lambda in successive orders m plus 1 and m just coincide, then from our grating equation what we can write is that a sin theta m minus sin theta I is equal to m plus 1 lambda, while for the other wavelength this would be equal to m lambda plus delta lambda. Okay. Now, if you solve this, then you get the expression of delta lambda. Okay. The wavelength difference is known as free spectral range, and this is given by lambda by m. Okay. It means that if we have two wavelength and their successive order m plus 1 and m coincide, then the separation between the two wavelength is called free spectral range, and which is given by equation number 50, and it is numerically if you can calculate it by taking the ratio between lambda and m. Once this all things are known, we can now solve an example here. The problem says if we wish to solve the two bright yellow sodium lines with a wavelength given by this and this in the second order spectrum produced by the transmission grating, how many slits must the grating possess at the minimum? Okay. What are given? The two wavelengths are given here, lambda is given and lambda plus delta lambda is given. The second order means m is also given, and what is being asked, how many slits the grating possess at minimum? At minimum the n is being asked. Okay. Two wavelengths are given, let us calculate the mean wavelength then. Okay. The mean wavelength is given by the wavelength 1 plus wavelength 2 by 2. Okay. This is now the mean wavelength. Why do we want to calculate the mean wavelength? Because we want to calculate the resolving power of the grating, which is lambda by delta lambda mean. If we want the number of slits to be minimum, then these wavelengths which are given here, they must be the minimum wavelength separation, okay, delta lambda mean. Now, two wavelengths are given, from there we can calculate delta lambda mean. Now, we will use the chromatic resolving power expression, which is lambda upon delta lambda mean is equal to m into capital N. Since m is equal to 2 and delta lambda mean is also calculated, lambda is also calculated, from here we can calculate capital N, which is 493.5. Hence, to see the two lines we need a grating with at least 494 slits, okay, which is the nearest integer to the calculated n. Okay. I would like to repeat again, if we relax this condition which is at minimum, then we will have several solution here, okay. But we want the minimum number of slit to produce this spectrum, okay. As the question says that we want to resolve two bright yellow sodium light, then whenever we say resolve means we are seeking delta lambda mean. Now, if we want to find delta lambda mean, then it means that we are behind resolving power of the grating. Resolving power is given by this, then we can easily calculate mean wavelength, delta lambda mean is known, m is known, from here we can easily calculate capital N. Okay. This is all for today. I end my lecture here. Thank you for listening me. See you in the next class.